Okay, so for this deep dive, we're unpacking a critical conclusion from all the sources. Solar cycle 25. It's not just active, it's accelerating way faster than anyone predicted.
It's really not a forecast anymore, is it? We have hard data. I mean, you just have to look at that severe G4 geomagnetic storm we had.
The one from the X5.1 flare back in November 2025.
That's the one. And it's a perfect example of the kind of volatility we're dealing with.
And if that wasn't enough, just a few days ago, on December 1st, we got another one, an X1.9 flare.
Right, which caused that instantaneous R3, that strong radio blackout, and put us straight on a G2 Storm Watch.
So this is the new normal, high volatility, back-to-back events.
Exactly. And what's really fascinating here is that the high-risk environment is sustained. The model's tracking the smooth sunspot number, the SSN.
Which is basically just a measure of how busy the sun is.
Precisely. Those numbers are staying high. We are looking at a peak risk window for at least the next 18, maybe 24 months.
Right.
Well into late 2026.
This is where it gets really strategic, though. It's the speed problem. That November X5.1 event, it launched a coronal mass ejection, a CME.
A huge cloud of magnetized plasma.
And it was traveling at, what, something like 1,500 kilometers a second?
An incredible speed.
Yeah.
And to put that into perspective, that velocity meant that the operational teams on the ground had only about 33 hours.
33 hours between seeing the flare and the G4 storm actually hitting us.
Yes. And when you're talking about critical infrastructure, 33 hours is almost no time at all. You can't deploy major defenses that quickly.
And the atmosphere itself is sort of primed for chaos, right? We're tracking the F10.7 radio flux, and it's high 138s Fu.
It is, and that indicates our ionosphere is highly energized.
Yeah.
So even a moderate storm, one we might have just shrugged off a few years ago during a solar minimum, is now much more geoeffective.
Meaning it can cause bigger problems on the ground.
Much bigger problems.
So let's talk about those problems. The specific failure mechanisms, because this is where it really lands. Let's start with the power grid.
The big one. These storms create what we call geomagnetically induced currents, or GICs, in long power lines.
And these are essentially rogue currents, right? They're not supposed to be there.
Exactly. They're a kind of quasi-DC current getting into an AC system. And when they hit those huge transformers, they cause magnetic core saturation.
It's like trying to force too much water through a pipe that's already full.
That's a great analogy. It causes overheating, and that can lead to permanent damage. But the immediate risk, the blackout risk, is actually a bit simpler.
The harmonic distortion, it messes with the protective gear.
It does. It causes the relays, the system circuit breakers, to mistakenly trip. One goes, then another, and that's how you get a cascading system-wide blackout.
Okay, so moving on from the grid, what about navigation, GPS, for instance?
Right. Well, the storm dynamically increases the total electron count, the TEC, in the ionosphere.
And that warps the satellite signal's path to your receiver.
It does. For a basic single-frequency GPS, like in your phone, that can mean positional errors of tens of meters. Your blue dot is suddenly in the next street over.
But for high-precision systems, it's much worse.
For them, the risk is scintillation. It's a rapid, chaotic fluctuation in the signal. The receiver just can't maintain a lock. Precision timing is just gone.
And finally, communication. The risk from the flare itself is instantaneous.
It is. The X-rays and UV radiation hit the D layer of the ionosphere, and it basically absorbs all the energy from long-distance HF radio.
A complete loss of coverage on the sunlit side of Earth, just like we saw on December 1st.
Yes, that R3 event was a perfect illustration of that.
So given all this, and the short warning times, what's the defense?
Well, the most critical preemptive defense is mandatory load management.
You mean just reducing power demand across the system before the storm hits?
Exactly. Lowering demand widens the system's voltage stability margin. It gives you the headroom you need to absorb that stress from the GICs without the relays tripping.
And long term, we have to be talking about hardening the infrastructure itself.
Absolutely. We need GIC mitigation tech, like neutral resistors, which physically block those unwanted currents from getting into the transformers.
And for systems that rely on timing,
they have to move away from single point of failure systems. That means multi-frequency GNSS receivers and, crucially, terrestrial backups like atomic clocks that don't need a satellite signal at all.
So the bottom line is, this high-risk environment isn't going away soon. It's here through late 2026. And since hardening infrastructure takes years, being proactive is the only real strategy.
Reactive measures are just too little, too late.
Which leaves an important question for you, the listener. Think about this. What's one critical sector in your life beyond the obvious power grid that completely relies on precise GPS timing that you may never have even considered? Maybe it's the synchronization of financial trades down to the nanosecond, or just how your local cell tower keeps the network running. The impact is so much wider than we think.